Roslin. Now, in this video, we'll see how we can define a lattice. Lattices. Firstly, we have to introduce something called posets. So, suppose if we have a set, we know that a set usually doesn't have any order for its elements. Okay, so this poset is actually an intuitive concept of an ordering, sequencing, or arrangement of the elements of a set, and how we formalize the same using posets. So for that, first we'll see what is a binary relation. Given two sets X and Y, their Cartesian product X cross Y is equal to the set of all ordered pairs small x comma small y, where small x belongs to capital X and y small y belongs to the set capital Y. Now a binary relation, usually denoted by capital R, over the sets X and Y is nothing but a subset of the Cartesian product X cross Y. A binary relation on a set X, we are just thinking about one set X, is again a subset of a Cartesian product, and here the Cartesian product is X cross X because only the set X is involved. So binary relation on a set X is the subset of the Cartesian product X cross X. Now a binary relation capital R on a set X is said to be, we are thinking about three terms. The first term says the binary relation R is reflexive if the ordered pair x comma x belongs to capital R for every x belongs to x. The next term is antisymmetric. That is, whenever xy, ordered pair xy and ordered pair yx belongs to capital R, the relation, that will imply x is equal to y. Okay. The third term is transitive. Transitive nature of the binary relation happens whenever the ordered pairs xy, comma yz belongs to capital R. That will imply that the ordered pair xz belongs to capital R. So you have a question to work on. Given the set A, B, C denoted by capital X, you are given three binary relations on X. See, R1, R2, R3. That these relations consist of ordered pairs, and definitely those ordered pairs, all of them are elements from X cross X, right? So this R1 is subset of X cross X, R2 is subset of X cross X, R3 is subset of X cross X. Okay. So that means they are binary relations. You have three of them. The question is nothing but you have to check whether R1, R2, R3 are reflexive, antisymmetric, transitive. So if R1 is reflexive, you will give a tick mark here, and if R1 is antisymmetric, you give a cross here, like that. So you have to fill in the spaces here. This is the question for R1, R2, R3. Now, a binary relation capital R on a set X is said to be a partial order if it is reflexive, antisymmetric, and transitive. So, a set X together with a binary relation capital R, which is a partial order, is called a partially ordered set or poset. And it is usually denoted as the ordered pair X comma the relation, binary relation R, which is a partial order. Okay. And normally, this relation R is notated as the symbol less than or equal to for our easiness. So you can renotate the same to get the definition. A poset is a set capital P with a binary relation less than or equal to, which is a partial order on X. That means the relation less than or equal to satisfies reflexivity, antisymmetricity, and transitivity. So you have a question to work on. You have a set P which is equal to set ABC, and you are given three binary relations like before. Here the binary relations are named less than or equal to 1, less than or equal to 2, less than or equal to 3. They are all subset of P cross P, right? The Cartesian product P cross P. The question is, which among the above binary relations on P are partial orders? So what you have to find is, you have to check if they are reflexive, antisymmetric, and transitive. If all the three of them are satisfied, then we can say that the relation is a partial order. So this is a question 3 for you to work on. Now, you have a poset ordered pair L less than or equal to, and suppose if S subset of L is an arbitrary subset. You have to note that it is an arbitrary subset. You can take any subset of L. Then an element U in L is said to be an upper bound of S. If for every S belongs to S, you have S less than or equal to U. And as a remark, we can note that a set may have many upper bounds or none at all. Okay. Now you have an upper bound U of S, and we call it a least upper bound or join or supremum if this upper bound is the least among all the upper bounds X of S. That is, U is less than or equal to X for each upper bound X of S. Again, we have a remark. A set need not have a least upper bound always, but it cannot have more than one. That is, if a set has a least upper bound, it will be unique. But we cannot say that it always have a least upper bound. In a dual sense, all these things can be said like this. We have a poset ordered pair L with a relation less than or equal to. For every arbitrary subset S subset of capital L, then an element small l belongs to capital L is said to be a lower bound of S. If for every S belongs to S, L is less than or equal to S. That means L lies below all the elements of S. You can think about it like that. The remark, as earlier, a set may have many lower bounds or none at all. Next, suppose if you have a lower bound L of S, this lower bound L is called its greatest lower bound or meet or infimum if for every lower bound X of S, X is less than or equal to L. X is related to L. And here also we have a remark, a set need not always have a greatest lower bound, but if it does, it will be unique. So to officially define a lattice is a partially ordered set in which every two element set A comma B, where A belongs to L and B belongs to L, has a least upper bound. That is, we have A join B and a greatest lower bound denoted by A meet B. That is, every two element set of the lattice L, they'll be having the supremum and the infimum. And just note how the least upper bound or supremum is denoted by in symbols. Similarly, how the greatest lower bound or the infimum is denoted by. Here, the symbol like this is called the join, and the symbol like this is called the meet. Now we have a remark which says the join and meet, that means the supremum and infimum, are binary operations on L. You have heard about binary operations when you are learning algebra, because to define a group we needed binary operations. A binary operation on a set L is a function from L cross L to L such that every element x and y in L, the ordered pair xy and the ordered pair xy, the image of the ordered pair xy is some element z in L. That is, f of x comma y is equal to z. Okay. So here we have the join or the supremum from L cross L to L such that the join of ordered pair x comma y is nothing but the supremum of x and y. Similarly, the meet from L cross L to L such that the meet of or the infimum of x comma y is equal to x meet y. And since for every lattice ordered pair L with the relation less than or equal to, we can associate a join and meet. Sometimes a lattice is denoted also as the order triple L comma join comma meet. So as an example, suppose if x is equal to the set ABC, consider the power set of this x, call it P, capital P. Now we are given a relation on this capital P. So P is our set. The relation less than or equal to here is given as subset of. Okay, this symbol represents subset of. So to analyze, you can say that phi, the null set phi is a subset of the null set phi. Similarly the singleton set A is a subset of singleton set A. Every set is a subset of itself. So definitely this relation satisfies reflexivity, right? Similarly, you can check the properties of antisymmetric nature and transitive nature. Both of them are satisfied. That means the power set P along with the relation subset of is a poset. Now we are going to check whether this poset will become a lattice or not. For that, you have to take a two-element set in the power set and associate a supremum and infimum for that arbitrary two-element set. So we are taking two elements from the power set of x, call them capital A comma capital B. I am assigning or notating the elements as capitals in capitals because here they are sets. The elements are sets in the power set of x. So here the supremum A join B will be nothing but A union B, and the infimum A meet B will be equal to A intersection B. So here the poset is becoming a lattice, and the same lattice can also be denoted as the order triple power set of x comma union comma intersection. So that is an example of a lattice. So the same lattice can be represented as a diagram which is called the Hasse diagram. So when you're viewing this Z diagram, you will have a better depiction of it in your mind. Okay, so here you have the null set phi, and here you have the whole set A comma B comma C. This null set is a subset of every set. So I am just laying this singleton sets before on top of this null set, and this line will imply that null set is a subset of the set C, null set is a subset of set B, null set is a subset of set A. Next, for setting above A, you can say that the singleton set A is a subset of the set two element set AB. Similarly, singleton set A is a subset of the two element set AC. Similarly, for singleton set B and the singleton set C. And then each of the two element set is a subset of the set we are considering. So this is the Hasse diagram of the lattice we consider. So the structure can be thought about like kind of diamond, or it has a structure like that. So that is why it is called a lattice, because we can associate that to the shape of that to such structures. So that's why it is called lattice. Now you have the question 4 to work on as check whether the following are lattices. Okay, the first one is the set of all real numbers scripted along with the relation less than or equal to in the usual sense, the normal sense less than or equal to. The next question is you have the set of all divisors of 6. Okay, and you are giving the relation of A less than or equal to B to be A divides B. That is 1 divides 2, 1 divides 3, 1 divides 6. Similarly, 2 divides 6. Similarly, 3 divides 6. So the that's how the relation comes. So you have to give the relation, what is the binary relation, and you have to check whether that also forms a lattice. So that is all for today, and let's see in the next video. Till then, bye.